Okay, so in this lecture, we're going to introduce operator algebra, and in particular, we're going to introduce it using Braket notation. So quantum mechanics is a mathematical framework written primarily in the language of operator algebra, and so this makes it really key to have a simple, compact, and yet expressive way to write down and talk about these concepts, and that is what Braket notation does for us. Now, there are three basic types of objects that we're going to come across when we are talking about operator algebra. So let's introduce them one by one. The first are scalars. Now, scalars are going to be just normal complex numbers, things like 1 and pi and 3. And we're going to write these just like normal numbers with no extra notation or bells and whistles. The next objects to talk about are vectors. So vectors are higher dimensional collections of numbers. Think of them like vectors in multidimensional spaces, but you can also think of functions as special types of vectors, which is something that we'll talk about. Now, vectors are going to come in two different flavors. On the one hand, you have right vectors, or ket vectors, and these will be written with a vertical bar, and then the symbol of the vector, and then a closing right brace. On the other hand, you have left vectors, or bras, and these are written the other way around. So now you have a sort of a less than opening bracket, angled bracket, the symbol associated with the vector, and then a vertical bar. And the final piece we have are operators. So operators play some of the most important roles in quantum mechanics. What they do is they transform a vector, either a ket or a bra, into any other vector. Operators in this class will be written with a capital letter, always with a capital letter, and they will always get a little hat on top. So it's the hat is what signifies it's an operator. The capital letter is just for redundancy. So before we start talking about these things further, there are a few ground rules you need to know about how operators and vectors behave, especially with regards to the normal rules of math that we're all used to and love. In the attached paper, there is a complete list of all of the normal properties of algebra and their definitions and which ones are obeyed. But it's really just one important property that you have to think about at all times, and that's the commutative property. So for real math, the commutative property tells you that the order of a lot of the mathematical operations don't matter. And so there's two particular versions of this. There's either the commutativity of addition or of multiplication. And so the example of that is that a plus b is equal to b plus a, right? So 1 plus 2 is 3, 2 plus 1 is 3. And that's what the commutative property means when you're talking about addition. It's the same for multiplication when you're talking about normal math, right? So 2 times 3 is the same as 3 times 2. Scalar math is just real or complex math, and so nothing changes there. But properties change a lot when you start talking about vectors and operators. So let's talk about vectors first. Okay, so for vectors, first of all, to add up vectors, you have to make sure you're talking about a ket and a ket or a bra and a bra. Adding a ket and a bra doesn't make a whole lot of sense. So you have to make sure that you're always using a ket and a ket. But if you're properly trying to add two kets, then that does commute. So ket A plus ket B is equal to ket B plus ket A. When it comes time to multiply, again, the exact identities really matter. So for example, if you try to multiply a ket with another ket, that doesn't really have a prescribed meaning in linear algebra, and so this is basically nonsense. Same goes if you try to multiply a bra with another bra. This is effectively quantum mechanical nonsense. So that means that there are two orders of this multiplication that do make sense and that we can talk about. So the first is a ket bra, and the second is a bra ket. But it is very important to note that these are not the same. In fact, as we'll see in a little bit, the ket bra represents an operator and the bra ket represents a scalar. These are not the same thing. Okay, and the last property we need to talk about, or the last category we need to talk about, are operators. So again, as you might imagine, operators do satisfy the commutative property when it comes to addition, which means that a hat b hat is equal to a hat plus b hat is equal to b hat plus a hat. And again, this might be obvious at this point, but this does not apply when you talk about multiplication. So a hat b hat does not equal b hat a hat in general. The consequence of this is that from now on, for all future equations that you see, you have to really suppress your inner instinct that says reorder multiplications in a way that looks appealing or that is intuitive. You can change the meaning, you can change a vector into a scalar, and so on, so you have to pay a lot of attention to the actual order in which you're seeing things. Okay, first we're going to talk about vectors in Braket notation. So this right here is a generic vector referred to as a ket, K-E-T. As we'll see, in quantum mechanics, all physical information is encoded in a complex vector known as the quantum state, which is written as a ket, just like this.
Let's start smaller. Let's start by thinking about a ket as a vector that sits in a 2D vector space. So this vector will sit somewhere in a 2D plane that looks like this.
And you may have seen this before in more of a vector notation. Whereas I hat is a unit vector that points along the x-axis, and the j hat is a unit vector that points along the y-axis. The E1 and E2 vectors are basically the same thing, and we're going to add a third way we can write this, where we can now write those unit vectors in Braket notation. So the way we're writing it here, this x ket and the y ket can both be considered unit vectors pointing in the x and y direction, or if you write them again as column vectors, they'll look like this. Okay, there's also a complementary vector that's important, which is referred to as a bra. If we stick to our example of a 2D vector space, if the ket is a column vector, then the bra should be a row vector. But you'll notice here that it's not just a simple row vector, it also gets this complex conjugation. So this is why there's stars above this. So there is a special relationship between the ket and a corresponding bra, and this is referred to as the adjoint. This is what the adjoint is. And the adjoint will be written with a dagger. And the way the adjoint plays in is that if you take the adjoint of the ket, and we'll write it like this, notice the dagger outside the parentheses. So we take the adjoint of the ket, then what we get is the bra. And of course, vice versa. If we take the adjoint of the bra, we get the ket. Now, if we combine this with this row vector that I wrote above this sort of easily implies that the adjoint of a scalar must be the complex conjugate of the scalar. So here's what I mean. Going back to original definition of the bra, we can insert this, we can insert the identity we used above. And then when we take the adjoint of this, then we can immediately see that psi1 adjoint must be psi1 star. So there are two special operations with bras and kets that we need to talk about. The first is the inner product. And the inner product is what you get when you multiply a bra times a ket. So this is such a special operation that we typically write it in a simplified way where we remove one of the vertical bars. So there's now only one vertical bar sitting between the two different symbols. And maybe as you've already picked up, this is actually the situation where the name for the notation comes from, right? Because if you read this left to right, you see braket or bracket notation. And the result of an inner product is always going to be a scalar. So some complex number. In the case of 2D vectors, then this would just look like a normal dot product between these two vectors, except that you're taking the complex conjugate of whichever vector corresponds to the bra. There's also a special version of the inner product, which is a vector with itself. And this is effectively a norm. And we'll typically give it a special symbol, which just indicates that it's the norm squared. So the other way this could happen is you could have a ket to the left of a bra. Now this has a completely different interpretation. In fact, this corresponds to an operator. So pay special attention that the inner product corresponds to, or the inner product results in a scalar, and the outer product results in an operator. And these behave completely differently, so we have to keep this straight. Okay, the next thing we need to talk about are linear operators. So linear operators are special mathematical objects that transform a vector into a new vector. What you see here is the operator A is applied to the ket psi, and the result is a ket chi. So in other words, operators take vectors as inputs and return vectors as outputs. In this class, we're always going to write vectors with an uppercase letter, and we're going to put a little hat on top to signify that they're an operator. Okay. Okay, so furthermore, in this class, we're only going to ever deal with linear operators. So what makes an operator linear? This is our first definition. So what this means is that an operator will be linear if you can apply the operator to a sum of two kets, and get the same exact result as summing up the individual contributions of applying the kets separately. And it's really important that this has to be true for absolutely any scalar and absolutely any vectors, right? So this is a property of the operator itself. It's not a property of which kets or which coefficients, which c's or which sides you're using this with. Okay, multiplying two operators gets you a new operator. To really quickly recap this, in Braket we have four distinct objects we need to think about: a scalar, two types of vectors, and an operator. And we can summarize the results of multiplying any of these things by making this table. In this table, we're just going to fill in the result of what happens if you multiply something from the column on the left by something on the column on top, or by the row on top. So if we multiply a scalar by a scalar, we should get a scalar. Okay, let's start by going across the first row. So if we multiply a scalar by a scalar, we should get another scalar. If we multiply a scalar by a bra, it remains a bra. If we multiply a scalar by a ket, it remains a ket. And if we multiply a scalar by an operator, it remains an operator. Okay, so dealing with a scalar is easy, and in fact, we're just going to copy the same stuff going down the first column. Okay, where things start to get tricky is when we start multiplying kets and operators. So going across the second row now. Going down the second row now, we multiply a bra by another bra. Then this operation really doesn't make any sense, right? This is what we talked about, or this is what we didn't talk about. This is neither an inner product nor an outer product. And so this is really just gobbledygook. Okay, but now if we multiply a bra by a ket, what we have here, we have a bra ket, which is a scalar. And then finally, if we multiply a bra by an operator, right? An operator is something that transforms a vector into another vector, and so this would remain a vector. Okay, so let's go down to the next row. So in the next row, on the left side, we will have a ket, and we're going to multiply it by first a bra. And so in this case, what we get is this outer product, and this is an operator. In the next case, if we multiply a ket by a ket, we're back in the range of nonsense. Finally, once again, if we multiply, and for the last entry here, having a ket times an operator is actually also kind of nonsense because everything is pointing the wrong way. So because an operator has to act onto the side with the vertical line, this is also effectively nonsense. So now let's go through the final row, and here again we're in the same situation. So this operator times a bra. Because the operator is not acting on the vertical line, this turns into what is effectively nonsensical. If an operator is to the left of a ket, This is a times v, and this just gives us another vector. So this gives us a vector. And then finally, if you multiply two operators together, then what you get back is another operator. Just like we talked about the adjoint for bras and kets, there is also a really important adjoint for the operator. Okay, and again, we're going to write adjoints using a dagger. So given operator A, the adjoint of operator A is written as a dagger. And again, the adjoint of the adjoint will give us back the original operator. Okay, so adjoints play a really special role in operator algebra, and the way you can think about them has to do with the order in which you apply things. The way to think about this is that operators, like the a hat, should always be applied to the right. So they always be applied to a ket. But the adjoint is the special version of the operator that you instead apply to the left. So let me give you an example. So let's say we wanted to compute this, what's called a matrix element. There are basically two equivalent ways we can imagine doing it if we have the vectors sitting around separately. So we could either first apply A onto this ket chi, and then we take the inner product between this new vector zeta and the original psi. So what we've done here is applied the operator A to the ket on the right, and then take an inner product of that resulting ket with the bra that's on the left. The other way we can imagine doing this is instead applying A to the left. But in this case, what we have to do is apply the adjoint. And if we do this, then we have an equivalent definition for this matrix element that looks like this. And you can make sense of this by taking this definition for eta and taking the adjoint of that. Okay, and then when you stick that back in, then you see something, you have a bra that corresponds to what you're looking for. Okay, so the way to think about this is that all operators should always act to the right, but the adjoint is a special version of the operator that allows you to act it to the left. So this is some advice. If you're ever in doubt about how to act an operator, which version of it you can move to the left or to the right or whatever else, then I would always go back to this ket form that we're shown here. So take the adjoint of everything so that you have operator acting on a ket, and then do all your math there, and then go back and later on take the adjoint of the whole thing, just like what we did in this line here. Okay, taking adjoints of operators is a special operation in itself, but it's actually very simple and very straightforward, and it never changes. So basically, the process is going to be, if you have some complex expression, so let's start with this example. So to take the adjoint of C, what you're going to do is basically read the expression right to left, and then write down the adjoints of each term left to right. So we'll go through this step by step. So going right to left, first thing we see is B. So we start with B, and then we add a dagger. And then keep going, we see A next, and then we put a dagger, right? So the order of the operators gets reversed, and you got a dagger to all of them. This works just as well as if you're talking about any complicated expression, including things that are effectively vectors or scalars. So if you want to take the adjoint of this expression, again, you go right to left. First, you see this ket chi. You turn that into a bra chi. And then this is multiplied by a dagger. Now let's imagine we have something slightly more complicated. So we want to take the adjoint of this more complicated object. Again, we just step through. So right to left, the first thing we see is this c, which is a scalar, and we see the c, which is a scalar, and the scalar, and the adjoint of a scalar is just the complex conjugate. The next thing we see is bra psi. When we take the adjoint of that, we get ket psi. Next we have ket phi. When we take the adjoint of that, we get bra phi. And finally we have a dagger. When we take the adjoint of a dagger, we get just a. An important consequence of the way this all works, and this is just based on the way the math is written, is that we have the following. So we reverse the order of everything in a matrix element, and we take the adjoint of the operator, then what we get is the complex conjugate of the original thing. Now, there are two important definitions I want to provide you that are related to the adjoint. So the first is the definition of Hermitian. So a Hermitian operator is one where the operator and its adjoint are identical. Okay, so in practice what this means, if you have an operator that is equal to its adjoint, is more or less that you can apply the operator either to the right or to the left at your own whimsy. And that ends up being really useful. But it also has some other really useful properties that we will be using later on. In particular, we will see that all operators that correspond to observables, anything that you could measure in real life corresponds to a Hermitian operator. And the related definition is that an operator for which a dagger is equal to minus a is called anti-Hermitian. Anti-Hermitian operators won't come up nearly as much in this class as Hermitian operators will, but they have some similar and related useful properties, and so they will come up from time to time.